Hi guys, welcome back to my mathematics tutorial. Peter, my name, and an instructor of mathematics at the University of Liberia. In this video, we'll be looking at an additional problem on a reducible to variable separable method. So when you watch previous videos, we discussed how we can reduce a differential equation of this form to variable separable method when initially we cannot easily solve the problem using variable separable method. So let's look at question number 75 under differential equations on all of our videos on differential equation. We have a playlist, so you can just scroll down the playlist on a ordinary differential equation from lesson 1 all the way down, so you can watch. They are in order. Now, so we have sine inverse of dy by dx equals to x plus y. Now, if we had this equation to be just equals to x, if this equation was just equals to x, it would have been very, very easy to solve because we would have gotten rid of the sine inverse by taking sine on both sides of the equation using the composition of functions. But you have plus y, which makes it a bit challenging for us to easily separate the variables. So as such, we observe it in this form and bring in a substitution for x plus y. That is, we say let u equals to x plus y. The objective is to ensure that at least we have a single variable on this side of the equation so that the problem can be reduced to separable form. So we differentiate both sides considering that u and y are variables or are functions, right? And then this x is the variable within the different functions. So we differentiate u, we get the u with respect to the variable within the function u, x. And we differentiate x is just 1. The derivative of y is also 1. But since y is a function as well, so we say dy with respect to the variable within this y function x. What's the next objective is to solve for dy by dx. So we send this one across, we have du over dx equals, let's say, minus 1 or equals to dy by dx. What's the next is to replace dy by dx now within the original equation. So we have sine inverse. What is dy by dx? It's now du over dx minus 1 or equals x plus y now is just u. To get rid of this inverse, we can take sine on both sides of the equation. So we know that sine inverse of an angle is equal to that angle. Or sine inverse of sine, let's say you have sine inverse of x is just equals to x. Sine inverse of sine of x is just equals to x as well. So whatsoever x is, whether it is a kind of whether it's of this form or whatever form x is just equals to x. So sine inverse of du over dx minus 1 is just equal to du over dx minus 1. And then on the right hand side is just sine of u. So now we can separate the variables. Du is equal to 1 plus sine of u, cross multiply. So is du equals to 1 plus sine of u times dx. Because this is the x, we don't need this 1 plus sine of u, so we have to get rid of it. We only need expressions that are in x. So we divide both sides by 1 plus sine of u. So this cancel. You have now du all over 1 plus sine of u. So we can integrate both sides to find our general solution. For the left-hand side, we can rationalize. So we rationalize by taking the conjugate of 1 plus sine of u. And the conjugate for 1 plus sine of u is 1 minus sine of u. 1 minus sine of u, right? The integral of the x is just equal to x. So whenever you rationalize and you are to multiply the conjugates, it ends up in difference of two squares. So for short, when you have two conjugates to multiply by each other, you just multiply their first terms and their last terms, because their middle terms will always cancel. So 1 times 1 gives us 1. And then sine of u times sine of u gives us minus sine square u. And the numerator is just 1 minus sine of u du equals to x. Now, what is 1 minus sine square u? According to the Pythagorean identity, 1 minus sine square u is equal to cos square u. So we have 1 minus sine of u divided by cos square u du equals to x. So we can separate the numerators. So we have 1 over cos square u du minus the integral of sine of u all over cos square u du equals to x. 1 over cos of u is equal to secant. So if you square it, it gives you 1 over cos square u, which is secant square u. So this gives us secant square u du. Next one, sine, let's say 1 over cos of u times sine of u over cos of u gives you sine of u over cos square u, right? So what is 1 over cos? 1 over cos is secant. So this gives us secant of u times sine over cos is tangent of u equals to x. So what is next? Okay, further, we find the integrals now. The integral of secant square u du is just equals to tangent of u. And the integral of secant of u tangent of u is just secant of u, or equals to x, plus some arbitrary constant c. So what is u? U is x plus y. Secant of x plus y. X plus c. So this is our general answer for this problem. Now let's quickly do another problem. Let's look at another problem. Question number 76. So we say dy by dx is equal to sine of x plus y plus cos of x plus y. So again, in order to have a single variable on the right-hand side of the equation, we must substitute x plus y to be some variable. So we can say let z equals to x plus y, right? We differentiate both sides to find dy by dx. So dz with respect to dx is equals to 1 plus dy by dx. The next goal is to solve for dy by dx. So we send this one across. It becomes dz over dx minus 1 equals dy by dx, right? Great. What's next? What's next? We'll go back to the problem. So where we see dy by dx, we want to replace it with dz over dx minus 1 equals sine of x plus y is just z plus cos of z. So we send this one across and separate the variables. So we have sine of z plus cos of z plus 1. So the z now equals, sine of z plus cos of z plus 1 times dx. So because this is x, and in here you have z expressions, so you must divide both sides. You must get rid of this entire expression because you only need x on this side. So we divide this side by sine of z plus cos of z plus 1. Again, we divide this side by sine of z plus cos of z plus 1. So this cancel. We're left with the z all over sine of z plus cos of z plus 1 equals to dx. We integrate both sides to find the general solution. Now, at this point now, we have to be very, very careful on how we find the general solution for the integral on the left-hand side. Several ways to approach this problem. So one way I could think on is to use the half angles identities. So we can find half angle identity for sine of z, and also we also know that there is an half angle identity directly for cos of z plus 1. Now let's look. We know first that sine of 2z is equal to 2 sine of z cos of z from the double angles identity. So if we divide each angle by 2, we get half angle immediately. So you have sine of z now to be 2 sine of z over 2 cos of z over 2. So where we see sine of z, we're going to put this expression. Next, what's about cos of z plus 1? Now we know that cos of z over 2 is equals the root of cos of z plus 1 all over 2. So we can solve for this cos of z plus 1. That is, we square both sides. So we square both sides, we have cos square z over 2 is equal to cos of z plus 1 all over 2. So we cross multiply 2 times, cos square z over 2 gives us 2 cos square z over 2 equals to cos of z plus 1. So we're going to use these two identities now. So we have the integral of dz all over sine of z is just 2 sine of z over 2 cos of z over 2 plus, what's next? Cos of z plus 1 is just equal to 2 cos square z over 2. All equals, the integral of the x is just x. Now, this is what we need to do again. We can divide the numerator and denominator by an expression that will lead us into something that we can easily integrate this integral. Remember, I told you there's no direct way. Now, note that if we divide both the numerator, the coefficient is 1, right? So if we divide both the numerator by cos square z over 2 and the denominator by cos square z over 2, it means that we have rationalized cos square z over 2. And why are we doing this? We notice that if we rationalize cos square z over 2, now what do I mean by rationalize? This was what I did. Cos square z over 2 divided by cos square z over 2. So if you look there, this can be rewritten in this form. That is, let's prove it. 1 over cos square z over 2 divide 1 over this divided by this, right? Cos square z over 2. Division rule says rewrite the first fraction, reciprocate the second fraction, and change the sign to multiplication. So if we change the sign to multiplication and reciprocate this, it means cos square z over 2 will come in the numerator, and down here will just be 1. So if we multiply now, we will have cos square z over 2 all over cos square z over 2, right? So this can also be written in this form. So we rationalize cos square z over 2. That was exactly what we did. Now, we didn't change anything in the problem. Let's erase some of these things. Nothing we changed in the problem. We only rationalize cos square z over 2. We didn't bring anything new. We rationalize cos, because this can cancel this. This can cancel this. So we did not bring anything new in the problem. We are only trying to make the problem look very easy so that we can be able to find a general solution. Now this is equals to x, right? So 1 over cos, we know that 1 over cos is secant. So this the integral of secant squares z over 2 all over. Now we distribute this cos square z over 2 in this term and in this term. Or we say we multiply this by this, we multiply this by this. So multiplying this expression by each term, we have 2 sin z over 2 divided by cos square z over 2. And then we multiply by the next term plus 2 cos square z over 2 divided by cos square z over 2. So this is dz all equals to x. So we can, because there are 2 trigonometric functions here, we can separate this cos square by saying cos z over 2 times cos z over 2. We just open it, right? So cos z over 2 cancel this one. Now we know that sine over cos is tangent, right? Also, this cos square and cos square also cancel. So what are we left with? We are left with the integral of secant square z over 2 divided by 2 tangent z over 2 plus 2. So this is the z equals to x. So 2 and 2, we can factor out 2. So we have 1 over 2 integral of secant square z over 2 all over tangent z over 2 plus 1. The z all equals to x. Now we know that the derivative of tangent is equals to secant square x. So if we differentiate tangent, we get secant square x. So you see, tangent gives us secant square x. So we can say let u equals to tangent of z over 2 plus 1. We differentiate du bar dx or du bar dz, right? Because it is z here now. It's equal to, so we send the z on that side, so we don't have to write the z down here. So du now is equals to secant square z over 2. And then we differentiate the angle. What's the derivative of this angle? It's like saying the derivative of z. Then you factor out this 1 over 2. Derivative of z is just 1. So 1 times 1 over 2 is 1 over 2. So there's the z that we're putting down here now. We can just bring it right here, the z, right? Because if the z was here, you would say the z times this. Just bring it on that side. So what next? Now, the derivative of 1 gives us 0, so we did not include it. So we can now multiply this 2 by this du. So that will give us du, 2 times du equals to secant square z over 2 dz. So wheresoever we see secant square z over 2, we're just going to write 2 du. So we have 1 over 2, the integral of 2 du, all over, and then tangent z over 2 plus 1 will just give us u equals to x. So this 2 can cancel this 2. The integral of the u over u is just the ln of u, or equals to x, plus some arbitrary constant c. Now, we can easily solve for this u. Before bringing in these values for u and that of z, we can solve for this u. Now we know that e raised to the ln of x is just equals to x. So e raised to the ln of any expression is equals to that expression. Similarly, if we take e on both sides, e raised to the ln of u equals e raised to x plus c. E raised to the ln of u will just give us u. And then we can separate the function, which is e raised to the power x, and the constant. So we say e raised to the power x times e raised to the power c, so that we can rewrite that e raised to the power c to some arbitrary constant. It doesn't have to be e raised to the power c, because it is still a constant. So we can just replace it with c or d or whatever constant we may select. So let's go. So we have u equals to e raised to the power x times c times e raised to the power c. Now we just take c. What is u? We saw that u was tangent of z all over 2 plus 1. So this is z over 2, or equals to e raised to the power x, or we say c e raised to the power x. Additionally, what is our z from the beginning? So we can rewrite the 1 first if we like, so that it doesn't confuse us, like thinking that this 1 is also part of this angle. So we write the 1 first. 1 plus tangent of z is x plus y all over 2, or equals to c e raised to the power x. So this is the general solution for the y by dx sine of x plus y plus cos of x plus y. So thanks ever so much for watching. Please subscribe to our channel and see you in our next lecture. Thank you.